recommendation algorithms that will suggest us what to watch and what we have to buy. And AI is all around us. And it is driving innovation in the healthcare, or might be in the finance, transportation, and there are countless other fields we have. However, with the great power comes the great responsibility. And we celebrate the advancement of AI, and we must also grapple with the ethical questions. How do we ensure that this AI system is are fair as well as unbiased? And how do we protect the mainly the piracy of our data, which has been driven in AI, and these complex issues has to be carefully considered. In conclusion, AI is a force in shaping our future, and further it holds incredible potential to improve our lives, but it also challenges us to critical thinking that we harness the power responsibly. Thank you very much.
Thank you, sir. I would like to thank CEO sir and Principal sir for joining this inaugural function. Today's inaugural function, our FDP. Thank you, sir. Thank you all for joining this function. So let us start today with the first day session. The first day session, our speakers are Christopher sir, and today one more session, afternoon session, internal speaker will be Dr. Manoj Challa sir. Kindly join. First, I would like to give a small introduction to our Christopher sir about our speakers for today. Mr. Christopher completed his master in data science at the University of British Columbia. He previously completed his postgraduate program in big analytics and optimization at INSOC, India 2019, and undergraduate studies in the field of computer science engineering in 2018. Experts in automated machine learning platform, image analytics, and developing data-driven solution to solve complex business problem through proof of concepts. Thank you, sir. We are great to have with us. Sir, you can start your session. You can take over, sir. Christopher, sir.
Thanks a lot, ma'am. I guess, can you guys hear me?
Yes, sir. Thank you.
Okay.
You can start.
Let me share my screen and yes. Okay. Can you see my screen?
Yes, sir.
Okay. Oops. Let me see. Okay. Great. Firstly, thank you so much. Thank you for inviting me over. It's an honor to present to you guys about what I'm going to talk, which is text processing and word embeddings. I think these are critical topics to understand what AI means, or what the LLMs which you use right now, how it eventually performs, is because it has good embeddings inside. Right. Thank you for that. Thank you for inviting me. I have so just like, maybe I'll start off with an introduction. I don't have a slide for an introduction, so yeah, my name is Christopher Alexander. You can call me Chris. And Swati ma'am and Manoj sir have been my teachers before. I was not a very studious child. I was the backbencher, and fortunately enough, I have got to a stage where I can say I know a little bit about AI. I have studied in some prestigious universities, pushing through, getting internals, begging for internals, and finally I'm here trying to explain to you guys what I know a little bit of. So thank you, Swati ma'am, Manoj sir, and the faculty at Gopalan for inviting me over. And I found memories with Gopalan as well. And let's get going. Just heads up, if you want me to talk a little slower, please interrupt me and tell me that you can go a little slower. And if you have questions, you can raise your hand and I will stop at any time in the presentation and we can have a question answers. I will probably ask you to skip a question if it's coming later in the slide. But if not, we will address that question right away. So please feel free to stop me at any time and we can get this like a Q&A in between as well, because I don't have specific slide only for Q&A in between. Great. Right. So today's agenda is the importance of text in machine learning or AI, right? Why you need it. And I'd also like to understand the audience. If this is not something that you have seen often, then I'll go a little more slowly and you can stop me and say, oh, Chris, I do not understand what this means, what features mean, what CSV doesn't mean. But if you are interested in higher end tech of the math and all of that, we can maybe dwell into that a little bit as well. So first step is importance of text machine learning, then a little bit of basics of text pre-processing in machine learning, of how to use text and what pre-processing methods you have to use, and then vectorizing data. That is basically converting your text into some way the machine can understand. Then we'll get into embeddings, we'll get into LLMs, transformers, and so on, and then we'll conclude. Right. Importance of text in machine learning. So text is unstructured data, right? Structured data is your CSV or your Excel sheets, which you have, which columns and rows, right? These are structured data. Unstructured data is just text. It does not have a fixed length, right? It has variable lengths. Like if you write a review, I can say, oh, the product was great. Someone else can say, oh, it was a great product. I like the color. I like so and so, and it goes on. They can even write pages. And so white text is unstructured data give context. It also gives you understanding of what they mean. Whereas if it's one thing, like let's say it's a rating, I've given rating 5. It just says rating is 5. It does not tell me why the rating was 5. But if I write a review, you know exactly what he means by the text in which he's giving, right? So it's a very primary source of information. It gives you context. It gives you the meaning behind data, which is why large language models text is the key right now. Right? And most of us, text is primarily source of structured data. Even on your Instagram post or your Facebook post, the captions mean something. Or in Twitter, it's all about text, right? There could be images and so on, but very primary source of structured data, unstructured data is text. Challenges is it is complex, right? It looks easy to you because you can read, you have learned alphabets, you've learned grammar, you've learned language, so it's easier to you. But for the machine, it's not. Right? It's just eventually you will see that it's just numbers. I need to understand numbers because the machine can understand only numbers. Right? So that's the most challenging part, to understand language, and plus even language in an extent where everyone can understand. So it could be simplex, it could be complex. Everyone knows different levels of understanding the same language, right? So those are one of the challenges. And advantages, I already said, 80% of the information in the world is mostly text. Right? It's slowly going to video and images with digitalization, but until now it is 80% is still text. Yeah, so basics of text processing. Why is it, why do you need to do it, right? Example, you don't need words such as to, from, where, here, all of that. So those kind of words, the connecting words, conjunction words, and to, those kind of words may not be useful. It might be useful to understand the context, but sometimes it's not. Right? So text processing is to remove all of these unnecessary words like commas, punctuations, full stops, right? Those don't give you much meaning. So remove all of that. And also to find root words, plurals, grammatical tenses, and so on. So I've just given a few examples of text pre-processing. I'm not going to dwell into the code of many things here. I'm going to give you a theory based with some examples of how everything works. But if you want me to show code, ask me. You can raise your hand, and then I'll see if I can show. I have some slide open, some notebooks open, and I can explain that as well. Right? Yeah. So some examples is tokenization, right? Like a simple sentence, "Hi, this is Chris," is consisting of many different words. Hi, this, and then is and Chris, and that these each single word is called a token. Right? You need to convert each of those words into tokens, and that's exactly what I've mentioned in the example. And then stop word removals is words I said which may not be necessary, common words, the, is, and so on. Stemming and lemmatization is you get the word into a root form, like running actually means run, right? Like the root form is running, the action verb is running. Right? The root form is run, action verb is run. So you can do that as well, some sort of text processing. Then convert everything to lowercase, the most basic way to make sure hello world is the same across both the places. Right? As a text classification thing, this is the most basic you will know to pick, given a text message, predict if it is a spam or not spam. Right? So your SMS is your column 1, target is your Y, the statistics X. The whole point of machine learning is you are learning the function of X variables. Here, maybe here it's SMS to predict Y variable, which is target, right? So this is a basic example of how it will look. Yeah. But the problem is machines don't understand this, right? So we need to convert this. And the whole point of vectorization of text data is that, is to convert this into some numerical form which the machine can understand, such that this numeric value means valued or urgent in the first line, urgent as a valued, that's right? What is each word in numerical form? That's vectorization of text data. Right? Yeah, exactly the reason why I said why you need machine learning models require numeric data. So you do all of those pre-processing, remove all of those punctuations and all of that, and then you try to make a good numeric input for a particular word. That's vectorization. So I'll teach you a few basic methods we'll get into, and then we'll get into word embeddings and so on. Right. First two common methods is bag of words and TF-IDF. I get to each of them one by one. And right. And another thing when you do this is you also make a way to make the number of features limited. Like if there's 10 words in a sentence, you get 10 words, but let's say you've got 100 sentences like that, but the sentence with the most number of length is, let's say, 100 words. So you can still make a matrix of 100 words or columns, and then you can make a fixed length. I'll show you how that works in the next slide. Right? So what is bag of words? Basically, a sentence is a collection of words. Right? So the bag of words algorithm or logic is pretty much the same. It's saying, don't look at it as a sentence, or look at it like a collection of words. Right? If you see that whole paragraph, I love this movie, it's sweet, and so on. You just count the number of times each word has occurred, and that will kind of represent your sentence. Is what bag of words is. It's very basic, but it's a way of converting your text to numbers, right? Yeah, it's very popular. It ignores the syntax and the word order. Like I said in the previous slide, right? If you lose the meaning of I love this movie. So movie and love are not related here. It's just saying, oh, these are the words, these are the number of times it appears in that sentence. It does not tell you what it means. What are the semantic? What does it mean by I love this movie? What is the meaning of I love this movie? No, it just says I is there, love is there, movie is there, and so on. It's very basic that way. Right? So it ignores the syntax. It ignores the word order. Right? It just contains the vocabulary. and it contains how many times or the presence of that word in that sentence or document. Right? And this is how it look, right? So these are the SMSs I showed you before. And when you do bag of words, when you convert that each word in that sentence and then count the number of times or if it's present, you'll get something like this. You can see that there are 6 rows, just the same data set which I showed. Now it has 61 columns, right? That 61 columns means out of all those all those SMSs you have seen, how many unique words were there? So that means there are only 61 unique words in those messages, right? So for each of those unique words, you put a column out there and you say, is this word present in this document or not? So a document is a collection of words, which is what this is showing, right? So the attributes become words and your rows are still the documents. And then it says this document contains so and so word, which what makes this document, right? Most of this data is zeros, you would see, because not every document will have every word, the words in the other documents, right? And you can store it as sparse matrices, an efficient way of doing it. If you want the function name of doing bag of words, it's called count vectorizer. Right? I just want to stop here and ask, these are all very basic. If it's very basic, it would be great if someone can stop and let me know. We can push through these slides quickly and get to the other important parts. Or is this good pace for now? I am not able to see anyone's input, but okay, I'll just keep going then. The next one is TF-IDF, right? It's an improvement over bag of words method. What it says is, oh, you're just saying a document is just collection of words, but what about some words will make a document very unique, right? So this incorporates the importance of a word in a document in comparison to the other words, right? So the formula is term frequency into inverse document frequency. Term frequency is the number of times a word appears in the document, right? Which is your previous slide. Let's say if it is always 0 times appearing in the first, always is the 4th row here, and 4th column, and the first row is not, so always is not appearing in the first document, right? So that is term frequency, what you saw is bag of words. Now, what you're saying is you also put in a metric for how common or rare a word is across all documents. So then your score changes to term frequency into IDF, and then that's another way of doing it, right? So this way a word appears rare or frequent. So the scores will change to this way, right? It won't just be counts. It will be how meaningful those words are, how rare those words are. Right. So both these ways of representing data just kind of solves your problem to say, okay, I've converted some words to numbers, right? And in that way, I have made the document with the number of words and that into numbers, and I can now do machine learning on. Right. It's very simple. It's easy to implement. You can do all of this, but it's not great. It's throwing English language out of the picture. Right? It is not teaching you, this is, I love this movie means I love this movie. It's just not, I and love are not independent. They are dependent in a sentence. Grammar is important. Information is conveyed through grammar and context and all of that, right? So there is no, it as bag of words, TF-IDF assumes there is no compositional meaning in language. It's just words combined to form sentence. But it just works for all these simple tasks where you have some few text columns in, let's say, big machine learning problems. It's easy to implement as well. I think this is pretty straightforward. Any questions until now? Just pause, ask. Okay, I'd assume that's a no. And okay, so the next step is introduction to word embeddings. Right, this is where the whole crux of things happen. So, like I said, limitations both don't capture any semantic meaning, be a bag of words and TF-IDF. Example, king and queen are treated as unrelated. It doesn't matter how it comes. So what is required for machine to understand language, right? The LLMs you see right now, all of them use word embeddings to understand language. That's the whole essence of LLMs, or all large language models, right? So what you ideally want in a scenario, or how you want to look at it is, oh wait, king and queen should somewhere be close. The numbers should be similar, right? Or let's say Gopalan and some other college RV should be similar, right? So that's what we're trying to do with vector representation. Dude, I don't want one number. Like you can increase the size of the numbers. You can represent word with a matrix, a length of like 300 different numbers, but give me more meaningful answers so that king and queen are pretty much similar in the numbers, right? So if you convert it, let's say instead of one number into like 300 numbers to represent one word. Now you're considering it as one word in a 300 different dimension space, right? And that should be, queen should also be in that 300 different dimension space closer to king, and is what you want. That's pretty much word embeddings introduction. What do you mean by word embeddings? Right. How this is done it's called distributional hypothesis. What it says is you usually know a word by the company it accompanies, right? Like by the company it comes with, right? Like if A and B are mostly in identical environments, like in this example, right? Her child loves to play in the playground. Her kid loves to play in the playground. So if you get tons of messages saying sentences like that, which says child loves to play, kid loves to play, you're trying to see how kids and child mostly come in similar words around it, right? That's the essence of distributional hypothesis. That's how it's framed so that you understand how to get these words in numeric form, which are similar. Right? And these are some basics which we need to understand first before we get into how word embeddings are being done, how to create word embeddings, how large language models are going to do it. Right? So the first, let's say these are three words: apricot, digital, and information. They are accompanied with two words, large and data. Right? So apricot and large comes together two times. Like the apricot is next to large 2 times. Apricot is next to data 0 times. I'm giving a very basic example. Digital is close to data 1 time. Information is close to large 1 time. Information is close to data 6 times. Okay. Now, if you represent this is a 2D is 2 dimensions, right? If you consider large as 1 dimension, data as 1 dimension. Now let's plot these words in that space, right? If you can see the graph, information is somewhere here, which is 6 on data and Y on large, right? And digital is here, apricot is here. Right. Now, let's see. So similarity, right? This is how do you figure out the words are similar? Because I can't compare a 300 number to 300 number, right? How do you figure it out? There are 2 ways, right? One is dot product. This is just mathematical way of dot product to calculate dot product of 2 vectors to see what the value is, to see if these 2 vectors are similar or not. I'm calling each of these words a vector because all of these are represented in different dimensions. Right? And you would see the dot product of digital and information is 6, right? And I'm not going into how you do dot product. I'm pretty sure you know it. If you do the same thing for digital and apricot, you'll get 0. So higher the value of the dot product, the more similar the words are. Right. This is the most basic way of doing how do you compare 2 vectors are similar. Right. But what happens is the information you graph. If you see information here, it is largely skewed. Right. It's, let's say the number of times information comes next to data is very high, because it's like a very long vector. but we actually don't need so much. We don't need to know the magnitude of that data. We only need to know how similar these two words are. So this angle between digital and information is enough, right? So what we do is we take the cosine of that angle between those two words, and that is also a similarity metric. And then the values would also range from -1 to 1, right? It can also be changed to 0 and 1 if you do it in a different way. But yeah, this eliminates the importance given to the number of times the word has occurred, right? Okay. This is how you do. This is how you figure out how similar two words are. Let's get back now. What is the problem with bag of words and TF-IDF is there is no understanding of how words are related to each other, right? So the first way of doing that in word embeddings is to understand, like I said, distribution hypothesis. You'll know a word by the how it appears with other words, right? So a term and term co-occurrence matrix is a matrix showing how often a word appears with the other words. Let's say these are the words in this graph, right? They're like 4,190 words, right? Machu and Machu appears 0 times together. Machu and Pichu happens 79 times, and Machu and Citadel happens 1 time, or Insa happens 5 times, right? This way, you're kind of getting a way to represent a word, Machu, with how it appears with other words next to it, right? So in this example, if you get, once you do this term and term co-occurrence, this is again counts, right? But it's with words with other words and how they appear, so that you get a good representation of the word alone, right? So if you do dot product between tall and height, in like let's say in it's not there, it's not shown here, but I'm saying if you do a dot product of this term and height, you'll probably get a value, and cosine similarity is 0.33. But the dot product between tall and official is 0, and the cosine similarity is also 0. So you're seeing that this term and term co-occurrence actually works, that it's kind of getting words which are similar, or at least getting similar scores, right? Right. So where are we at now? We can get some meaning from between words. Like we can understand how one word means with another word. Okay. But if you see this, this is 4,000 rows with 4,000 rows with 4,000 columns. So that means there's 4,000 words only in this small data set I have. How much words are there in the world, right? How much? There's going to be millions of words, right? So the columns are going to be huge. We'll have millions of words. One way to do still get some embedding is you do PCA, principal component of analysis, or you do singular value decomposition to get these co-occurrence matrix to make embeddings of each word, right? This semantic meaning is created, like I said, this meaning is created only for our data set. It's not fully accurate. It is based on what data you give and what data you've made that matrix with, right? But we don't want embeddings which are just king, which is represented in a way that only by the data I have given. You want king's embeddings to be in a way that it is represented across all the data in the world, right? So what we want is we don't want all of these we don't want to king represented by 1 million other words. We want something with 100 dimensions or 1,000 dimensions, let's say, right? We want it condensed, dense, but it also has to be rich. So those are the drawbacks of these term co-occurrence matrix, right? And we want something which is generalized. We don't want it to be data set specific, so that it can help in practice as well. And I mean, because ML models, or let's say large language models, we don't want to train weights for a long period. We want small condensed weight. If you make each word to be with 1,000 dimensions, you're reducing the weights from 1 million to 1,000, right? That's a lot. I need to pause here. Any questions? I want this to be interactive. Anyone, if this is good, because we'll move into, these are the most basic ways. I want you to understand why we're getting into what is embeddings. And so that when we go and we deep dive, no, we don't get stuck of why we're doing this. Any questions? Anybody? Okay. Right. Okay, so deep dive into word2vec. So all the reasons I gave you, we don't want something to be not generic, right? So I want something to be generic. So let's see how that works. Before we dive into how do you build that, let's see how it looks. Right? So this is how this is. I'm just taking some code snippet of what I have, right? And it's a word2vec model trained by Google on Google News data. Like it's taken all the news which go in the world and it's trained all the models on that. Right. It has 3 million unique words. Right. That's the size of the vocabulary. And its next step is each word. Right. Like this is my college. On the left, if you see, this is UBC. Each word has a dimension of 300. Right? So each word is represented by 300. And these words are trained on Google News data, right? So this is a huge amount of data. Yep. So, and now you can, these embeddings are almost ready to use, right? Because now you can compare, let's say I'm comparing Canada and hockey. You'll get you, so this is just a function given by Google's thing as well. You can just directly call similarity. It's probably going to do cosine similarity or dot product inside, right? And you will see that it's Canada and hockey are 0.27, where Japan and hockey are 0.09. So you see that this hockey is because Canada plays a lot of ice hockey. Japan doesn't play a lot of ice hockey. So you see the similarity between how often is Canada and hockey written in the news. Right? It's pretty accurate most of the time. You can even compare. Let's say I compare UBC with CMU, right? Carnegie Mellon or University of Toronto. You'll see the scores really high. Right? So this is how the dense word representation works. Like one word is represented into 300 dimension, right? How do you build that? That's or how it's built in the backend. That's what we're trying to do. That is word2vec, right? We want it to be general so that anybody can use. Now I can take this data and just feed it into a machine learning model and try to get good. It's way better than what we have done with first with just words, then with saying words and word comparison. Now we get to generalize, right? Like I said, out of those words, million words and other million words, you can do PCA, which is a dimensionality reduction technique. And LSA is another way of doing PCA without centering. And then you get embeddings of, let's say, I want embeddings of only size 10 or size 100, right? You can do PCA with components equal to 100, and you can get dimensions based on that. But the problem is it's still data centric, right? So we don't want to do that. The alternate approach is to use the popular word2vec family of algorithm, where it's done using training neural networks. And it captures meaning because you could see that hockey and Japan are related. You could see colleges being compared with different colleges and they're related. Right? Let's get to how that works. So word2vec is a family of algorithms, right? I'm going to just teach one algorithm out of it, which is skip-gram model. So a skip-gram model is a neural network, right? It is a neural network to obtain this dense representation of words to get embeddings, basically. And how the logic works is given a target word, and it's, let's say, given just a word, you try to predict its surrounding words, right? So that the hidden layer which has becomes like the weight matrix is a good representation of trying to predict that word. Let's take an example, right? Add freshly squeezed pineapple juice to your smoothie. That's the word, right? And let's say your word you're trying to do embedding for is pineapple, right? That's your target word. If you have a window of one to just say see one previous word and the next previous word, I'm going to give input as pineapple and trying to train the network to predict squeezed or juice, which is your context words, right? So that the embeddings which you generate are going to be representative. Pineapple is going to be a representative of all the words that came around it. And it's going to be dense if you train it with millions of text messages where somewhere pineapple is there, right? So if you see in this example, like I said, juice is target word is pineapple, and these are the contexts. Juice is likely to occur with pineapple. Squeezed is likely to occur with occur in the context of pineapple, right? How do we do it? Is a neural network. It's an input layer, a hidden layer, and an output layer, and then we use a softmax at the output layer. Okay. Yeah. So this is the skipgram model architecture, which is your input layer. I'll explain it with a better example next with words with the same apply freshly squeezed pineapple, right? So it's just for the architecture people who are interested. This is input, and then there's a hidden layer, and then there's output layer. Right? There are multiple output layers because it's Y1 is to say context is context for one other word, right? So if a pineapple and you want to predict juice, that's Y1. Y2 is pineapple, you want to predict squeezed because that's the previous word, that's Y2. There'll be so many other context words, right? Different words. So just showing it a different way. Right. I'm not going to go into the math totally, but yeah, there's going to be some math, and we'll just try to understand the logic, right? So this is the script grammar. It is, let's say there are 10,000 words in your data set, right? I'm just giving an example, right? In the world, there's going to be so much more, and then there's going to be so much, way more data, right? Because we are not going to train anymore. Nobody's training to get embeddings anymore, right? We just take embeddings which people have trained on Google, Amazon, Facebook, right? And then we use that, right? So this is how it works. Let's say we have 10,000 words in that corpus. And we're trying to get each word to be represented in a 300 dimensional space, which I showed you before. And the window size is 1. Right? You're just going to see the previous word and the next word. You're not going to see 4 words before or 4 words later. And that is still a parameter you can tune. You can change the window size and the tune, right? And then they do that and they train as well. So the first step is to convert first step is to convert each of this 10,000 words into a one-hot encoded form, right? You know one-hot encoding, right? It's 10,000 words. If it's pineapple and pineapple is at the index 800 row will have 00000 and 1 at one specific spot. It's just binary numbers. Yeah. Let's say there's a one-hot encoding of the word pineapple at index 800, right? If you see this spot. And you're going to have this blue portion is what you're trying to learn, which is your word embeddings, right? Yeah, one sec. Right. So once you do that, so you're going to have a weight matrix for your input layer to your hidden layer, right? Your input layer is 10,000 words. 10,000 is the size of your vocabulary. 10,000 is the unique words you have, right? 10,000 is the input layer. Your hidden layer is going to be 300 neurons. I'm just showing you, you have to visualize it. 300 neurons. And your output layer is going to be another 10,000, right? Because you're trying to predict another word. 10,000 with one specific word being true. So if it's 800, 800 means 0001 at 800, it means pineapple. And 5,428 is going to mean juice, right? 8,000 is going to mean pineapple. 5,428 is going to mean juice, right? So if you see the weight matrix now, you will have one weight matrix for the hidden layer, from the input to the hidden layer. So that's your weight matrix W. So that's going to be your size of 10,000 words into 300, right? These numbers are going to be randomly initialized first. And then when we train the model, it'll slowly improve and it'll be a good representation of each word, right? It's going to be 10,000 into 300. That means each word is, so let's say at 800 index of this matrix is going to be the vector representation or dense vectors of pineapple, right? And this is that weight. And WC is the weight between the hidden layer and the output layer. Okay. This is also going to be of size. It's actually size 300 into 10K. I didn't get a better example to show, which is, it's very simple. So just assume that it's V into D for now, and we do a transpose when we multiply. But when we multiply here, right, and to get the output, but it's 300 into D. Right? So this is again words, and each row represents one dimension, and then the words are the columns, right? So and then you're trying to predict the output is 0001, where 1 is at 5,428, which means it is a juice. Any questions here? You're getting a one-hot encoding of pineapple. One-hot encoding of 10,000 words means there's going to be 10,000 values, and at location number 8,000 is going to be 1. That represents pineapple as one-hot encoding. The same thing for juice. It represents at 5,428 is juice. You're going to feed in this input X for pineapple, and you're trying to get predictions where you're trying to get juice, right? And you're going to feed in multiple words like this: pineapple juice, pineapple squeezed, pineapple cut, and so on. Like you're going to train like millions of words like this with all the sentences you have got, right? Because pineapple used in different sentences around the world, right? And then you train the network. You train the network to a specific set of laws, and at end you will get a good representation of a word, pineapple, which is W. We throw away WC, which is your context. We don't want that. We only want W. We take the weights. The model is not useful for anything else but to train, and then you take W. That's how word embedding matrix is calculated. Any questions? Or do you want me to explain again? Anyone, please let me know so that I can. Yeah, I think someone has a question. Please go ahead. I think it's Gopi Krishna. Can they unmute themselves and speak, or how does this work? I don't think. Okay, let me see if I can unmute you. Yeah, I can see you, but I can't hear you. Yeah, I'm trying to unmute you. Now, can someone unmute Gopi Krishna, please? Ma'am, I need some help here. I can't help. I can't unmute actually. Okay, I'm going to explain a few questions. So this is Jammula Krishna Rao asked me to explain again. Can you type in the which one do you want me to explain? This whole part again? The chat.
Mr. Gopi Krishna, I think you can unmute. Access is given to you as a presenter.
Okay.
You can unmute and you can.
Yeah. Perfect question. Okay, I can explain this again. How do you know the exact number of hidden neurons, right? So that is the size of the embedding you want to give. You can usually it's trained on size 300, right? So you see here, it's this way Google trains this web-to-vec is of size 300. Right? It's something that the organization will decide if it is the hidden layer is 300 or 500 representation or so on. It's usually 300. And Google's decided for this word-to-vec model, it's 300. Skip-gram word-to-vec model is 300. Most models are 300. And it's based on that. Okay, on a high level, you want me to explain again. Gopi Krishna, can you ask a question? I still cannot hear you. You have to unmute yourself. You can probably type in saying that I don't know what you're trying to say. Okay, you'll type it in. Okay. I'm going to go back and explain this on a high level again. Jamula, and then you can tell me if there's anything specific you want to understand, right? So yeah, it is. So let's say this is one of those lines which you have, right? Which is one of those sentences you have. Add freshly squeezed pineapple juice to your smoothie. Right? And the other one could be add pineapples to your dessert. Add pineapples to my breakfast. Right? Add pineapples and apples together. Right? This could be multiple sentences like that. An organization is going to take the whole world wide web, internet, newspapers, the books, textbook, research papers, anything, get all the text we have. And it's going to train it in such a way that it's going to represent each of those words, unique words, right? And right now we assume that the unique words is only 10,000, right? But it could be millions. But this is a one-time process just to make one good embedding, right? So it's let's say assume it's 10,000 words, and we want to make an embedding of size dimension 300, right? And we are going to only understand a particular word by the word it comes before and the word it comes after, right? So that is the window size, which is 1. You can also consider 2 or 3. So in that case, I will do pineapple, and the output will be freshly, or a pineapple and then smoothie, or 2. That will be if it's Windows 3 or 4, right? I'm going to go with basic example, window size is equal to 1. You have 10,000 words. One hard coding of 10,000 words you would do, which is basically convert each row, each of them, let's say pineapple, Chris, pineapple, and so on. Let's say Chris is the first one. So it'll be 1000001 at 10,000. And then it slowly goes down till everything becomes 1, right? And so pineapple is at index 8,000, let's say. And so it's going to be 0 zeros or, sorry. Okay. Yeah, it's going to be 0 0 everywhere except 1 at the index 800. You're going to have the word, and you're going to have hidden layer, which is 300, because you have had embedding size of 300, right? This is going to be randomly assigned. So let's say when I choose pineapple here at 1, index 800, you are actually leaving out all of the other rows because you're going to only get the embedding at index number 1, index number 800, right? So if you see this 800, 0.13, 0.03, and so on, you're only choosing that embedding. But now you're going to multiply that with the weight matrix of the output layer, which is going to be 10,000 into 300 again, right? And you're going to get a value for that word, pineapple, with all the words around it, right? Because this is the shade, this is weight matrix of every word in a 300 dimension space again, right? Once you get this, you do a softmax, you do a softmax, and then you want to predict in such a way that 5428, the values here, which you've got, 5428 is the highest value. Right? If you do a softmax, you basically want to predict 1 in that place, which is at the word juice, not at the word pineapple. Usually, you'd want to do pineapple. Yeah, I think someone's asking something.
Now mic enabled in the from the mobile phone, sir. From laptop, I was unable to unmute.
Right. Okay. Just let me just finish this. Maybe I'm almost done.
Okay.
Right. So you try to get and predict juice, right? And you will do this for different words of where pineapple and different other words come together. And finally, you'll get a good representation of pineapple in every context it is used around the world, around every word, every sentence, right? That's the whole idea of this model. If you didn't understand specific part, you can put it in the chat again. Yeah, Gopi Krishna, please go in.
Sir, very nice explanation. But how we know the exact number of hidden neurons or hidden layers in order to predict the exact data, sir? One go, I think we may not get the expected values. How we know the exact number of hidden neurons or hidden layers, and what is the training?
Okay, yeah. So you're asking how did they get to 300?
Yeah. That's what, sir.
Yes.
So we
so that's
hidden neurons.
Yes. So the hidden neurons is something that they would experiment with again. So your hidden neurons is basically the weight matrix you want, right? What dimensions you want your weight matrix to be in. You can be in 500, or you can be in 1000, or you can be in 300, or whatever range you want, or you can even be 10 or 20. Right? There's something that they would experiment at some point. They have experimented at some point, and this model is optimized in such a way that it's 300 was the best hidden layer for the hidden layer, right? But if you want to, if they're releasing another model tomorrow, it might be 500 with 500.
That means it's already pre-trained network, sir. That means
yes, yes. I'm explaining you a model which is already pre-trained, how these embeddings are created, right?
Okay.
Yeah. The whole idea is even the transformers and embeddings, transformer layers, and all of that. Once they create those embeddings and so on, if you're trying to use it at some point, we're not going to build those embeddings again, right? It's what someone else will do, because even if you want to make these embeddings, we can't. We don't have that much data and resources as well.
Okay, thank you.
I hope. Okay, hope I answered your question. Jamula Krishna, he says he's got it. Anyone else with any other question? Because this is the most basic embedding. We will go to the disadvantages of this and so on as well. Okay, I'm going to continue. Right. So once you get these words, right, how do you evaluate them and so on, right? You can plot it up. You've got 300 dimensions, do PCA or do another dimensionality reduction technique and plot these embeddings, right? You can see how words are similar to each other, right? You can see that if you see in this, you can see these are all states of Canada: British Columbia, Alberta, Nova Scotia, Saskatchewan, Quebec, Canadians. All of these are states. You'd see that all of them are together. You could see avocado, mangoes, pineapple, citrus, avocado, so on. All of these are together. And so on. These are all names, right? These guys' names are together. So this is great. You have got embeddings which can show you get words together which are similar. But this is all the word level, right? How do you use it? And obviously you can increase the limit, which I said you're just considering one word before, one word after. You can consider 2, you can consider 3, you can consider way more 10, right? They would have considered that, and then only they would have built the model. I am only showing you the working of how it works for one window, right? They would have trained the model on 10, 20, and extra, so many more, right? Which is why you've got such good representation, else you can't. And so, like I said, you've got embeddings for each word. Now, Chris, but the problem is it's still a document. It's a sentence of words, right? How do you do it? How do you use this embedding? Two basic approaches, right? Let's say this is your sentence, all empty promises. You take the embedding of all plus embedding of empty and promise and then do average, right? Just do an average of that. So you would get 300, 300, 300, and then you get an embedding space of all empty promises at a 300 dimension vector, but you average 3 words together, right? Next one is you just stash them all together. 300, 300, 300, now it becomes 600, 300, 600, 900, 900, right? 900 dimension word. The problem with concatenating is your dimensions go way beyond, right? So you still have to, again, do dimensions you have to bring it from whatever the size of the dimensions is after concatenating embeddings for each word into some other fixed space, 100, 200. You'll take only you have to convert it by PCA or TA or some other dimensionality reduction technique. All right. So you can do this. This was what the world was doing, let's say 6 years ago, right? But the word embeddings are static, right? The embeddings are the same, irrespective of how the words are used. Example, right? If you see here, the word bank has the same embeddings for river bank, even if it's used in river bank or it's used in Canara bank, right? But these are two different meanings, right? The embeddings are great, but it's been trained on all of this. It's trained on river bank, Canara bank, and everything. But still, the embeddings for bank is still going to be the same, right? It's trained on all of that, and you're going to use that same thing. And so what we need is the embedding has to change based on how it is used, right? So we want to understand the contextual meaning of what a word means. So understanding context is what language is, right? To understand river bank is different from Canara bank. We went to English class and we figured out, oh, this is how these words will come around. But how do we make the computer learn that? Right? That is what we're going to see next. That is what LLMs or transformers would do. Right? I think I'll just quickly recap what we've gone through. Right? We saw first representing documents as a bag of words, right? Then we created documents as embeddings of words. We did embeddings of words, and then we concatenated them or aggregated them, right? Before that, we also saw how to get embedding of the word just with respect to what word it occurs in a document, right? Term co-occurrence. We figured that we want something general. So let's use something which Google or Amazon or someone has trained. But how have they trained? They have trained using word-to-vec skip-gram model, right? I have explained to you how word-to-vec skip-gram model works, right? And then you get embeddings for each word, concatenate them, and you get the sentence embedding. Problem with it is it does not have contextual meaning. It's the same embedding irrespective of how the word is used, right? We would go to the next slide. Anyone with any questions over this whole process before we move to the recent years, last 10 years, last 3-4 years of how the world's doing embeddings? I'll quickly see the chat if there's anything. Right. Okay. I don't see any. Okay. So what to act to modern LLMs, right? All of us are here to learn on Gen AI, generative AI, right? So how did it get there? Because we wanted to understand language, like how we understand language. We don't want it to understand just like, hey, it's not just collection of words or how it comes with respect to words. right? Which is the need for transformers, right? So now so the intuition, right? The need, you remember the properties we wanted. We want that the words and how they come in the sentence matters. So the order matters, right? If you also want representation of a word saying if bank is coming next to river, that means this. If we also want a long distance dependency, like let's say I have a sentence, Chris is working out today, and then I continue to say he also worked on, and so on, right? So I have to get like the context of he is who, right? At that some point, I'm just giving very simple example, right? So we also want long distance dependencies. So if someone's saying pineapple is squeezed at some point, and then we say pineapple is being transferred into another bowl, it has to understand it's squeezed pineapple, right? It's almost like how we understand when we read that text. We'd be like, oh yeah, pineapple was squeezed before, now it's being transferred to some other bowl. So the pineapple is no more just sour pineapple, it's squeezed pineapple. And so you want to understand long distances dependency on what text is. And then the contextual meaning, which I said, how you want to use the words. So I'm going to quickly skip to transformers, right? But the world has gone through different phases of where it is right now. It started with Markov models, hidden Markov models. It went to recurrent neural networks. It went to LSTM, right? And then they said we still need a better way, right? And that's when we went to transform. Markov models were able to represent the time, like to represent the long distance dependencies in text, right? The assumption in Markov model is the future is conditionally dependent on the present given present, right? I've put in a lot of text in all of these slides, and I've also put in notes. So I will share these slides at some point to everybody. The reason for putting the text, a lot of text, and making it so boring, or sometimes where you guys cannot see a lot of images, is because it's just you just can read through these slides at some point and see if you can understand something, and then you can research more, right? So that's why there's a lot of texts. So there's notes as well. I've given in this slide a presenter notes that will also be shared. You can see and you can read that. So Markov models is basically saying if given a word, it's conditionally dependent on what words upper before that, but it's just it gives you a time factor, right? And then RNNs had to understand memory in a different way, how to understand these memories, how much of long distance memory do you use? Do you use everything of what you know or you use little bit and so on? All of these led to the main major problem is it's hard to optimize all of these. And to train all of these RNN is sequential, right? You want to learn one text and then goes another text and so on. So it's problematic. So in came transformers. Transformers is a type of deep neural network. It's used to handle all these sequential data and capture these distances. It is the state of the art right now. But it's based on two specific main innovations. First is self-attention, position embeddings, and encodings. Just get into that now. Right. So this is the transform architecture. This is kind of the architecture is your chat GPT, your chat, all of these LLMs which you're using, right? This is how embeddings are created, right? And on top of this, there are other things, definitely. But these are your transformers and how it's being used. I will explain the block, right? This is your input. Inputs are still tokens. I have mentioned what tokens are. You'll have an encoding, it'll go in, and you're trying to predict next word or so on, right? So these are stacked transformer blocks. The whole idea of this graph is to say that, oh, it happens sequentially. It doesn't matter. We are trying to get sequential way of doing this so that we can train faster. We can train more. We can understand language as well. And attention, right? Attention layer is the most important thing here. You'll understand this graph better when we move to the next slide. Now, this, again, I'll come back to this. We are going to focus on something called a self-attention layer, which is the most basic unit of the transformer block. All of these other things, layer normalize, feed forward layer, again, Linux, all of this you can understand on your own. Right? These are deep learning concepts. If you do a course on Coursera, to understand all of this, right? But self-attention layer is what we'll explain now. Okay, theory again. So how does it, what is self-attention? It's basically, it's inspired by us. Imagine you're reading like a news article about a recent election, right? When you're reading the whole newspaper, you'll not pay attention to the section where it says the candidates policies. You'll pay attention to the candidate policies and so on, but you'll not pay attention to how the election procedures are happening and so on, because you want to know about the candidate, right? You want to know about the candidate in that article. So the other things you'll just read, but you'll not want to remember too much, right? You just want to understand the whole passage. You don't need how the election process is happening. You just need how the candidates' positions are. That's what we do, right? It's attention. What we pay our attention to specific things. So when we process information, we selectively focus on only parts of the text, and we want the LLM or the neural network to also look at data like that, right? So there's an example here, but I think I've already given you an example how it works, right? You want, and so self-attention mechanism allows the neural network to attend to different parts of the input text with varying degrees of focus. Like I said, there's at a given time, the model has access to all the inputs, and it'll be considered as one, right? Let's move to the better part. Okay, I'm not going to show the architecture and show you all of these math matrices and so on. It's going to be complex, and you'll just, I don't do it myself. I don't try to learn that. It's just not useful. You understand the concept, great, because you're not going to train an LLM from scratch. You're going to only fine tune. There are ways to do that now. You wouldn't really do. You just need to understand the working, right? Okay, so I mean, we can definitely train an LLM from scratch. We are teachers, scholars, PhDs. Like, yeah, that's the whole goal. We improvise on this. We understand learning and make something better. Sorry for that statement. And but yeah, let's say the example is guitar, string, melancholic note. Right. I want to get an embedding so that a note is a representation of, to understand context, right? To understand, excuse me. Right. So we need to understand context. Like I want to understand meaning. Note should understand, even note is not just a note. It can also mean music. That's what this means. This is a note and this is musical note, right? And I want the embeddings to change. If it is a musical note, I want a different embedding. If it is a writing note, I want a different embedding. That's the whole idea, right? That's what we wanted. So let's say this is the sentence you have. I'm just showing how it's going to train. You have all of these embeddings, right? These are going to be not defined at the start, or you can even use your word2vec embeddings, right? And then you can train on top of that to get context. That's pretty much what they did. But yeah, all right. And then you go to dot product. This is embeddings for note. Each of these words, let's say there are multiple words before this as well. This is from left to right. Now I'm trying to get the embeddings for note, right? Let's focus on note. I'm going to multiply note with every word which comes before it. The embedding of note and the embedding of melancholic, embedding of note and note as well, embedding of note and string, embedding of note and guitar. That's the dot product. You get the score for all of that. And then you'll do a soft max on this, right? And it's basically, you'll get score for each of the, what you're trying to do is you're trying to get the Y note, which is embedding of, you see on top, which you're trying to get the embedding of note with the embedding of each of the words which happened before that, but also how it happens before that when word occurs after it. Let me repeat. We're trying to get the embedding of note in such a way that it not only not only incorporates the embeddings of words which occur before that, but occur when note is the current word. That is what this dot product means. I'm not trying to get just the embeddings of melancholic or embeddings of guitar. I'm multiplying the embedding of note and guitar. So you see, note is being multiplied with every embedding, right? And then I'm doing a softmax, right? So this will give me a score. This is giving me a score of what is the embedding of guitar when note is appearing after it. So a alpha of note comma guitar is 0.00375 is saying the embedding of guitar, sorry, the embedding of note when guitar, sorry, one second. The embedding of guitar when note is appearing after it, right? And so on. This is the same thing for all of this. Right? Now you've got a score for each of these embeddings. Right? Now this is the score which I get told that guitar is being modified when note is coming afterwards. Take that score 0.00375. You take that score and multiply with the actual embedding of guitar, which is this green thing. Get it? And then you plus the score of this, which is note of embedding of string, with the score which you've got of the embedding when note is coming after it. You sum all of that up, you get an embedding now, which is the embedding of note based on all the words which come before it. But in addition, you're also understanding the embeddings of it in proportions to when note is being used. I think this is the most critical part of understanding this. This is attention layer working. All the matrices will confuse you, but this is what it means. I can explain this again. Any questions, please go ahead and ask. See the chat. No questions, but can I get an yes? Is people understood at the high level at least? Or is this over the roof? You want me to simplify it again? Okay, I get an yes. I get one yes. Thank you, sir. Thank you so much. Okay, 2. Great. Okay. Let's move then. Right. So this is how embeddings are calculated by LLMs right now. Right. That's self-attention layer. But this is just one small step into it, right? Let's get to the next slide. Okay. Logically great. Right. Now you have got, so I'm just mentioning exactly what I've mentioned in the explanation. The dot product of with all the previous tokens, softmax to get the probability distribution of scores, and the weighted sum of the inputs seen so far, and so on. But if you observe, each of the in the process of so each of these embeddings play 3 different roles. It's based on the embedding of note, which is the current focus, right? And the current focus of the attention, whether compared to all the previous inputs, there's also the key, and then there's value used to complete the current focus of attention. I'll show you what it means in the later slides. I'm not sure if this is okay. Again, I don't know if this was being hit all this way, but yeah. So there's going to be 3 roles each embedding plays, which is a query, which is the key, and which is the value, right? I'll show you in the slides how it works. And each of this is going to have 1 weights. It's going to be 3 weight matrices, let's say WQ, WK, WB, right? So each of these embeddings play 3 different roles: query, key, and value. This is kind of showing you how the math, right? This is the understanding. Now let's get to how the matrices work, because this is very important to understand query, key, and value, because that's how the paper is written as well. You need to understand that. Great. So nothing fancy, it's pretty simple. So let's focus on the note, right? The note right now is what is being calculated. We are trying to calculate the embeddings for note. I've said that's going to be matrices. Let's say, you see these 3 dots. Let's say these are all embeddings of all of the embeddings of all the words. Right? So at this stage, note is your key because it's what you're going to be calculating on. Note is your key. It is the current focus. And you want, like I said in the previous graph, you want to compare note to note as well. And you want to compare note to its previous words, melancholy, string, and guitar, right? Let's just keep this in mind. Just this layer, this dot product layer, because that's what's the first step here. So note K is query into note query into note key. Right? Why this is being done is so that, remember I said that we need to parallelize training, which is why this is done, right? So the embeddings are always available to all layers. It's always available to every training session. Like you don't have to train one sentence and then keep another later and so on. The embeddings are available to everybody, and once it trains, that's updated. Right. So you will get a note K value, and then you're pulling that from the weight matrix WK for the weight matrix for note K, you're pulling note K. And then from WQ, you will get note Q, because that's the weight matrix for note when it is in a query stage. Then at this step on the next is you need note is the query you want, and melancholy is the key you want, right? Melancholy key, and then note query again. Same thing, note query again, and string K. Remember, string K means it's going to be fetched from the weight matrix, which is of key, and note Q means it's going to be fetched from the weight matrix of query, right? So at a given time, it's not fetching from the same embedding, but 3 different embeddings. It's probably the same, but when training happens, these weights will change, which is basically telling you this is context, right? And the neural network also learns that, okay, this is how I need to update my weights when I do back propagation, when note is used with melancholy and note is used with string, right? Because the optimization is going to be done at the end layer. So this is key, query and key. You get the same value, which I said, soft max, sum all of them up. That's your output vector. Just the mathematical representation of the same logic, which I said. Right? Okay. If you understood this part, I'm good. I think this is what the most key part is, to understand query, and then key is just, if you read it up, you will also figure it out. And I've also put in the notes. You can read the slides and then you can get it. Right. Any questions? Anybody want me to stop, explain again? The chat. Okay, I think we're good. Okay. Right. Next slide is, okay, you have got embeddings. Great. Now, I said there's another thing. That is what you saw, all of this is self-attention layer, right? To get embeddings. But I also said there's another thing called positional embeddings, right? If you see, transformers, the 2 main innovations are self-attention to get contextual embeddings, but also positional embeddings, right? Or encoding. So what it says, this is pretty much very basic of what you can do, right? I also with the word want to put in which location it appears. Is it at the starting? Is it at the ending? Or like give orders to the number of words in a sentence, right? first word, second word, third word, so on. The most basic way you can do is add another embedding for just the weight. So ending with a melancholic note, right? That's your example. Ending is the first word. Second position is with. 3 is for A, you give 3. Right? This is another embedding of, let's say, dimension 300 or 200 or so on. Add it to the embedding of ending, and then you do the whole thing. Right? I would just, it'll be, I think this is a good starting point. If you want to get to the math of it, we'll have to have another session, so on. It's a little too deep. But yeah, this is how the paper explains it as well. Right? It's just saying you add another embedding, concatenate both the embeddings and say embeddings with position integrated in it. Right? During training, the embedding, let's say, of the first word is initially random vector. And then when you refine it with time, the positional embedding also gets encoded into, and then that also gets improved. That, okay, usually A and then another noun are going to be starting words and so on. Right, so you encode the positions also into it. That's what basically this slide means. Right, that's another innovation which they've done. It's an addition, just addition to, you add it to the embeddings and then do self-attention. Right, so now I'd like to go into attention blocks. Right, so now let's go back to this diagram. You have understood that this is a transformer block. This is an attention, right? This is the attention layer. All of these above things is just propagating data, push the embeddings up and all of that. Very simple, basic neural networks. Once you got the attention, if you see this graph, you see it says stacked transformer blocks. What you have learned right now is just one block, right? You've learned one block. Take it there. The whole idea of transformers, since you can parallelly do things, is you stack all of these up. You can just have multiple layers of these, and that's how it understands great context. That's what I'm going to explain next. Right? It's no more understanding of how it works. It's just like, okay, this is how it actually gets the embeddings, right? Position embeddings, right? Why do we need this, right? Like I said, now the embedding of note is not going to be the same all the time, but it's going to be different for every time based on what word is being is chosen on, what words is coming before it, right? So consider this example. Embeddings are in transformers, embeddings are not fixed. The vector representation of word varies depending on the sentence it appears in. Right? Consider the sentence: he went to the bank to deposit money, and she sat by the bank of the river. Right? These are two different. Bank will have different. Now bank in word to vec had the same embeddings. Right now it will have different embeddings for both these two sentences, reflecting different meanings. Because that's how the embeddings are calculated. You saw how it was calculated, right? It's calculated differently every time. So a single attention layer is usually not enough to capture everything, right? Like I said, what you just saw is one attention layer. What large language models right now use is, we call this multi-head. One attention layer is considered one head, right? It focuses on, let's say, only what you just saw right now is just semantic meaning. Okay, I understood words with respect to how, I understood a little bit of, oh, when juice comes, how does it work with words around it? I understood a little bit difference, context of bank in different ways of how it can come. But if you want parts of speech, you want to understand grammar, you want to understand synonyms of bank, you want to understand different other English language, right? As all computer science, what we did was great. We just said, stack it all up, make two different layers of each of it, and each layer will learn something. That's what neural networks also was, right? The hidden layer, each neuron will learn something in CNNs, right? Something like that. So you add multiple self layer attention layers. You call that heads, right? And then you will understand parts of speech, you'll understand every other aspect of relationship between inputs. Right? Let's also look. What I showed you was one layer, head one. But you send the same layer to let's say the inputs, you take inputs of, you take embeddings of all these words and you send it across multiple heads. You'll get different embeddings and you learn more weights, right? The whole point is learning the weights, right? And then you get understanding of different, you project it all down, you get one word embedding. Like you get one embedding for Y, right? This is multi-head attention layer. The other thing would be, let's get to this slide. Yeah. It's a multi-head. This is two things you got to understand. What is a multi-head and what is multi-block? Let's get this second. So if you can, I don't know if I can mark, but let's say you see these colors, right? You see this arrow here, this one arrow here, and then this one arrow. You see there's no arrow between each of these blocks, right? Because all of these blocks use the embedding from X1 or X2 or so on, right? These use all of these use the same embeddings to start that attention layer. To start, you see this? All of these are passed to different heads. Head 1, head 2, head 3, all of these use the same embeddings. So from the same text, they're trying to learn different meanings. Or same embeddings, they're trying to learn different meanings of how to calculate based on what it comes. But in multi-block, once you learn one attention layer, you pass that whole embeddings, learned new embeddings to the next layer, right? So that's what is a multi-block. This is another block. This is one block, this is another block, this is another block, but within them are multi-heads, right? So again, this is going to be just theory, just to understand that. Let's take an example, right? The first block, which consists of multiple heads, right? In real life, that's how it is. It may just understand just syntactic roles. Let's say one attention layer, one head will consider semantics. One might consider long range dependencies. One will consider parts of speech and so on. Right? That is multiple heads in one attention layer. You consider all of that, you aggregate all of it, and then you send it to next block, which considers another multiple attention layers. Now this layer is now going to build upon, oh, I know the meaning of each word based on how it appears in a sentence, based on all of that. Now let me understand the relation, let's say let me understand what is a verb, what is an action verb, and so on. Like I'm just giving you very logical explanations of how you can understand. So when you block all of these, each block is going to improve from the previous, and you'll try to get meanings, which is why now generative AI can give explanations which man cannot give, or some people cannot give, right? Even I don't have that much knowledge. Is understanding that, oh, Gen AI means generative AI means Gen AI. It can be used in a technological context. It can be used in a English educational context. It can, all of that is because we have fed in so many layers and says, learn whatever you want. Which is why the biggest problem right now is Google trying to figure out, I do not know how bias is coming in my data. I do not know how Google is how my LLM is supporting a left wing or a right wing. It's supporting blacks or it's supporting whites. I don't know how, because the data is what I just gave. The training is you learn various layers. So this way, when you do this, it understands context, then it understands what these words mean, verbs, then it will understand political scenarios. It will understand, okay, usually when a black thing is written or someone is written with respect to some race or this thing, let's say if all the news articles are suppressing one race, that's also data which goes in, right? So it understands this race and this problem. They're linking both of them together, right? That's where the bias comes in. There's so much other, that's the biggest problem which they're trying to solve right now. And so that's how multi-block is the essence of learning these embeddings, right? once you do that, this is how it looks. And I think we're almost done. Right. So once you get all these very, very good embeddings and so on, you get a question, you take that embedding, compare it with, make that embedding up in the backend. That's what happens. Take the embeddings of each word based on what words are coming. So if you give a question, I want to learn about artificial intelligence, it's going to get the embeddings of artificial intelligence based on I want to learn. Right? That's what transformers build embeddings, like they build embeddings like that every time you ask. Take those embeddings and then it'll generate output with a probability distribution again, because now you've got, okay, if I've got, this is the question, what is the usual answer? What is the next word which will come? Given these 10 different words, I want to learn artificial intelligence, what is the next word which will come? And so on. Now I'm giving you word example. It will go on a sentence level. It will go paragraph level, right? But essentially it's all a token. It's a word and how those embeddings are created. That's how it answers your question, right? Yeah, that's it. That's a lot of speaking, and I hope you've understood something at least. And I probably conclude if there's no other questions. Anybody? Any questions? Okay, you can go back and look at the slides. You can read through it, and then there's a good starting point to to learn more, right? And then we can do wonders. That's the whole idea, right? So the conclusion. What are the things we learned? We learned how text processing was important. We learned how the most basic sense, bag of words, TF-IDF, these are basic models, doesn't understand semantics, all of that, doesn't understand concept, contextual things. And we got word embeddings, gets a different, understands meaning between words, how words are used, but doesn't understand context, grammar. Evolving into transformers, self-attention teaches you how embeddings should be dynamic based on how the words come. Multi-head understands helps you understand different parts of speech and so on. Multi-block helps you understand bias in the world, helps you understand different context, right? Multi-block is the actual block which is happening right now, which people don't know how to solve, which biases and so on, right? That's pretty much it. Yeah, that's it. I guess that's it from my end. Thanks to everyone. Thanks for listening. I went very theoretical because going into the math would just blow people off the roof most of the time. Hope this was interesting. And any other questions, any general AI questions, anything, I can answer anything, whatever I can answer to my capacity. You can just have like a general chat on AI or what do you think is happening or anything like that. That's it from my end.
Right. Thanks, Christopher. Just dear participants, if you have any questions, please feel free to ask. You can type in your questions as well. Right. Thanks a lot, Christopher. I know it's quite late. It's quite late and it's midnight for you, but still you accepted the invite and you shared your knowledge with him. I hope our participants have got to learn a lot from the knowledge that you shared. Looks like there are no questions.
Right. Yeah. Thank you, sir. Thank you. I think it's
no question.
Is there any
Thanks,
questions?
Chris. Thanks a lot.
Yeah, thank you. I don't think there's any question. I will share my presentation. Thank you, everybody. Thank you, Karthik sir, for inviting me. He's been my mentor for so many years. Thanks to him, I'm actually here at some good place in life. So I'm very grateful to him. Yeah, thank
Thanks,
you.
Christopher.
Thanks, everyone. Thank you.
Good night. Thanks.
Thank you. Thank you, everyone.
Thank you. Dear participants, now let's move on to our next session for the day. We have with us Dr. Manoj Challa. Dr. Manoj Challa is the Vice President of Vice Principal of Gopalan College of Engineering. He has received his Bachelor of Engineering degree in Computer Science and Engineering from Madras University in the year 2000. Uh, he has completed his ME in CSE from Madras University in 2003. Dr. Manoj Challa has completed PhD from Sri Venkateshwara University, Tirupati, and his research interest includes artificial intelligence. He has total 22 years of teaching experience and has been associated with GCEM, Gopalan College of Engineering and Management from 2023 as Vice Principal and Professor. He has worked as Associate Director, HOD, Head of Cyber Security, Center of Excellence, and etc. in his years of experience. He has published total 28 research papers in international journals and conferences. He has published 10 patents. He has received leadership awards in the year 2020-21 from CMR Gnanadhara Trust. He is a IEEE member and life member of Indian National Science Congress. He is also spoke of Smart India Hackathon for 2018 and 2024. I request Dr. Manoj Challa sir to take over the session from here on.
Thank you, Karthik. Hope I'm audible.
You're audible, sir.
Thank you. Thank you. Thanks, Karthik, for the brief introduction about myself. So, yeah, good afternoon to one and all who are present here. The next session, as I'm taking up, so I'll just brief about the generative AI. The generative AI. So I'll take you through the theoretical part of generative AI, where the evaluation, what are the opportunities, and how can we explore with respect to generative AI. And in the next day sessions, we have real-time applications with respect to generative, where Mr. Abrar will be handling that particular session. So here in this session, I'll just cover the generative AI concepts and also a few case studies as well. Is my screen visible to all? Thank you. So I think I need one message. I got one message from Ramesh. Give you 5 minutes break. Do you really want a break or should I need to continue? If you want a break, I can do 5 minutes break and we can start by 11:55, 12. Okay then. So we take 5 minutes break. So by 11:55, we'll try to start the session. I request everyone to please join. If you're logging out, please rejoin the session by 11:55. We'll take 5 minutes break. Yeah, good afternoon to all. So we can start the session. I think I've given the required break as per your request. So we'll proceed with the session. So hope my screen is visible, right? Thank you. So good afternoon, one and all. So we'll have a brief discussion about this generative AI. So I'll take you through the brief history and the evaluation, and also what are the challenges, what are the limitations we have with respect to generative, and a few applications where we can use, and the case studies. So I planned up to 45 to 1 hour, 45 minutes to 1 hour presentation. So hope it will give you a brief introduction about generative AI and a brief knowledge, understanding about generative AI. And in our third day session, we have Mr. Abrar, who will be taking your live case studies with respect to generative AI. So coming to the agenda for my session today. So I planned with start with the basics of the evolution, the introduction, and what are the limitations, what are the benefits, what are the few applications. And I've taken one case study with respect to our academics, because we are all faculty and we are teachers. So I've taken a case study with respect to academics. If possible, we can do some group activity if it permits. And we'll see what are the ethical concerns we have while using this generative AI and what are the future trends. And finally, I'm going to conclude. This is the flow of my presentation for next 45 minutes to 1 hour of session. And coming to start, let's start with the artificial intelligence. I think everyone might be, most of you might be aware of this. See, a system that shows the behavior. So how the human intelligence interrupts. That's what we call it as an artificial intelligence. How the human intelligence is going to interrupt. So in that way, we can define that as an artificial intelligence. So, and there'll be some set of rules, patterns that can work. So where AI will be seen the most of the intelligence, where we're going to apply the intelligence with respect to defined rules and patterns which we can work. And if you are using any one of these, you might be using the AI concepts like Google Translator or this Alexa, etc. These are the few tools which are being used by using the concept of AI. And coming to strong artificial intelligence and weak artificial intelligence, a strong artificial intelligence is something like exactly to think like a human. It will think like a human, like it can be a commander data or terminator, anything. So which is real creativity and can even have a sense of purpose. So we can call that as a strong AI. And we have weak AI, that is weak artificial intelligence. So it is contained with a very narrow task, like a system processing language or text or pictures in your way. I could give from examples. So even ChatGPT or Bing or Siri these are the few examples we have with respect to weak artificial intelligence, where it will think in a very narrow task. Under the umbrella of this artificial intelligence, we have a lot of technologies. We can see machine learning is one of the main technology we can use, and robotics as well, and natural language processing, NLP, and also we have generative. Let's see, that is what our topic today, generative AI. So this is one of the umbrella under artificial intelligence. Under artificial intelligence, we have machine learning, we have robotics, we have robotics, and we have natural language processing, and also we have generative AI. So let's start with the generative AI from the evolution. So this concept has been traced from machine learning, and it was introduced late in 1950s, and it was explored the concept of using algorithms to create a new data. And the first example of generative AI, Markov chains, where it is a very popular one for the statistical model, which were used to generate a new sequence of data based on the input. And the machine learning is being popular or shine between 1990s and 2000, when advanced hardware and digital data becoming more widely available. And the birth of this generative AI, as we know it today, it is known as typically advanced type of machine learning known as neural networks. So as we know, it is from the machine learning where it calls the neural networks. And the creative power of generative AI comes from a specific type of neural networks called generative adversarial network. That is, we call it GAN. So it has been proposed by Ron Goodfellow and his colleagues in 2014. So this is one of the creative power of AI, which comes a specific type of neural networks, which we can call it as an GAN, that is GAN. And around the same time, the other forms of generative models like VAE, that is variational autoencoders, and recurrent neural networks begin to demonstrate their abilities to generate the content, making specific steps towards the field. And the evaluation, as we have mentioned, it has a lot of vital moments which has been reshaped to the landscape of generative AI, which has been reshaped to the landscape of generative. In that, the first one is WaveNet in around 2016. This is mainly used for the significant advancement in generative models for audio. So where we can generate realistic sounding human speech, which open the doors for more human-like AI assistants. So we call that as a wave network, where mainly it has been significant for advancement in generative models for this audio, where the realistic sounding human speech can be enabled through this. And we have progressive GANs. So it has been a milestone for high resolution and photorealistic images. This is one of the model where we can have high resolution and photorealistic images, where it is able to generate images from unpredicted details and also adding layers during the training of the process. So where we can get high resolution to train the system. So we need some high resolution systems. So we can, by using this progressive GAN, we can get the photorealistic images. It was in the year 2017. And we got GPT-2 and GPT-3 in around 2019 and 2020. That is generative pre-trained transformer model, a significant leap in the field of generative AI. That it demonstrates the ability to generate the sentence for making them useful for the wide range of applications, chatbot populations, etc. So this is nothing but GPT, that is generative pre-trained transformation. So we started with generative has been started a vital moments with WaveNet, where it is a very advanced version of audio, where you can get realistic sound human speech, and progressive GAN, where it produces high resolution photorealistic images, which can be used for the training purpose. And we have GPT-2 and GPT-3 in the success years of 2019 and 2020. There is generative pre-trained transformer. So where it can demonstrate a sentence which will be useful for the wide range of applications, writing assistant, chatbot, etc. And we have DAL-E, that is in 2022. It has been published, public, and it has been a deep learning model that generate digital images from the natural language prompts. So that is one of the, again, a milestone with respect to a generative AI. So it deals with the digital images, which can be useful for us to train or to present any particular scenario. And we have ChatGPT, maybe famous, everyone might be using this currently exclusively. With ChatGPT in around 2022, OpenAI released ChatGPT, a chatbot-based GPT, and a platform reached 1 million users within 5 days. So it has been very exclusively used by different users at different levels. And also we got the next version, that is GPT-4, that is in 2023. The latest GPT model is more accurate and advanced reasoning capabilities. A premium version of ChatGPT can be accessed this GPT-4. So in GPT-4, you can get any number of different accurate data with proper reasoning capabilities, but we should have a premium ChatGPT user, which can be an optimal access for GPT-4. So these are the other few milestones where we can have digital images by using DALL-E, and we can have a proper conservation chatbot, ChatGPT in 2022, and we have GPT-4 in 2023. And just introducing about generative AI. So generative AI refers to a type of artificial intelligence. It is a type of artificial intelligence that has ability to generate the content in many cases. The content that can be created by humans. So for example, you take ChatGPT, you can create a different types of contents. If you want to write a mail, if you want to write a report, if you want to write the contents, if you want to see the contents of the newsletter, audio, video, anything. So it refers to one of the type of artificial intelligence. So where we can generate the content in different cases where the human can create. So there is a basic thing about generative AI. And this generative AI operates by learning patterns and structures from large data sets that are used to the knowledge to produce a new content. So it has been trained by different patterns and structures from large data sets so that it can produce the new content, content which can be useful at different levels, at different cases. So what is generative? How does we have seen what is a generative AI, where it can give a comprehensive content which can be used at different levels, can be video, audio, images, or a text format. So, and how it can be used is, first we have to properly train the system through depending on whether it is in text, video, or audio, or the combination of anything, and develop different algorithms to categorize this, to learn from it, to train that one, and can train generative AI for generating the new data which can be used by the content which has been released by the generative AI. See, like the first thing is, as I mentioned, the collection of the data. This is how it works. First, we have to collect the data from different data sets. So huge volume of data. It's a huge volume of data. I repeat again, it's a huge volume of data from different data sets. Then we have to model training. We have to do the model training with the available data from different data sets. Then the data has to be generated. And finally, we have to evaluate. This is how it works. First, we have to collect the data, and then we can train by using different model training, data generation, and finally, with respect to the evaluation. So coming to the benefits, as I told, I'll just take you brief about the generative AI, general knowledge which we can get through generative AI. So the benefits what we can get through generative AI is, the first one is speed. It can handle, as I mentioned, a data collection. It can handle huge volume of data. Which cannot be done by a human at the appropriate speed. So the more complex data also it can handle and it can give. The next one is idea creation or content creation. So can generate new ideas and content that was previously not considered by the human. So content, what type of contents? For the same topic, you can get different types of contents, different versions of contents, where it may take time for a human to come out with these contents or creations. So that also can be one of the benefit. That also can be one of the benefit from generative AI. And resource generation can be used for dataset generation, modeling, forecasting, and all these things. And interface, it can provide the ability to interact voice, chart, images through multiple cases or multiple scenarios. These are the few benefits of generative AI. And also we have some limitations. We have some limitations with respect to generative AI. The first one is the quality and coherence. That is, sometimes the content which has been produced by Gen AI may be incorrect or not incoherent. It may not be accurate. It may not be accurate because at the end of the day, it is a trained model. At the end of the day, it is a trained model. So this can be one of the limitations. So the quality, sometimes it is not incorrect or incoherent. Lack of understanding. Sometimes the system may not understanding the question given by the human or by some other model. So it doesn't truly understand sometimes in some scenarios what exactly it is required. So deep understanding or common sense reasoning may not be happen in this generative AI sometimes. For example, in ChatGPT, if you give anything which is related to a personal question, you may not get an appropriate answer. So that means that the deep understanding is lacking here because it may not understand or may not think with respect to common sense where a human can do. And safety and privacy. This is also one of the limitations which we, in some cases, AI can generate a harmful content. So which may not be ethically used, which may not be ethically used. Maybe if you want to type, because it can give any type of letters, any type of context, it can be there, and content it can be used. So sometimes the safety will be less and the privacy will not be there. Anyone can get that data, can get the different versions of the data or different versions of the data for the same topic. And inconsistency. So inconsistency. So it is something like different responses at different time. So as I mentioned, the same topic can be given in different ways. So sometimes will lead to some confusion or inconsistency to choose the best one. So even though, again, I'll take the example of ChatGPT, you can get different versions for the same question what you have asked. So inconsistency is there. So still, we can take that as a limitations in some scenarios. And over generation, these models can tend to over-generate the content. So it can have many content sometimes which is not required by the user, So you'll get more number of content it can. So these are the few limitations which I can express with respect to generative AI. The next one is data dependence. Exactly, it is completely depending on the trained data, what is being trained by the model. So from which database you are doing. So it is completely depending on the data which has been trained. And for example, there is a limited and biased data training can result in poor performance. We have a ChatGPT 3.5, for example, only has data up to September 2021. These were the records. So that means you may not get the accurate or the exact information as of today if you're using ChatGPT 3.5. So as per the records, so the data is there up to September 2021. So the data dependency is there. Still, I can consider it as a limitation because the dependency is on the data from the different sets. So prompt sensitivity, the way a prompt is framed is significantly impact the output. So effective prompt requires skill and experimenting. So maybe it can be the frame, it can be the template, or it can be a structure, a pattern which can be used. It depends only on that particular significant prompt. So because of that, it may affect the output. Because of that, it may affect the output. So then coming to the challenges, we have seen some limitations. When coming to the challenges, so challenges is the cost. First one. So it may be a high computing cost. So the environmental, the climate, where you have to come out with the different conditions. So the cost might be one of the challenge thing. And data, as we seen, the one of the limitation with respect to generative AI is data dependency. So not enough data. You should get huge volume of data till date to get a accurate information, to get an accurate information. So or the data which has been existing can be biased, So one more challenge is reliability, must be human supervised, or even the tools may not be accurate, and because it has the prompt, the structure based or the pattern based. So the reliability is also one of the challenge. And the ownership, who is going to own the content which has been generated? So suppose if I'm taking some content, who is the owner of that particular? So ownership is one of the challenge. So should people disclose the use of generative AI? Yes, it is a generative AI because of to manage the things. We cannot put a blame on the vendor or something. So we should think properly before using that particular data. So this also a few challenges: cost, data, because we may not have the sufficient data. We should have huge data, and the reliability, and also the ownership. These are a few challenges which we have, which we can have in generative AI. And safety, as I mentioned, safety and highly esteemed abilities and unpredicted outcomes, data security. So all these things are challenges, unpredicted outcomes. Sometimes you may get some data which may not related to your context. So that also can be one of the challenge to prevent that. And obviously, as I mentioned, security, privacy, data security is always a concern with respect to the generative AI, one of the challenges. Then identifying the opportunities for Gen AI. So what we are trying to generate. So the nature of the task. So we should use it properly if you are going to try with an opportunities, what we are trying to generate. So for each and everything, we should not depend on that. So what is the nature of the task? Is it really required to use the Gen AI, the ChatGPT, or any other tools to get the content? Complexity of the task. Does it need to broke down into the segments? These are one of the opportunities that can be. So if we have more complexity, we can use the concept called modularity, where we can divide the complete problem statement into different modules and solve it. So we can call that as in segments as well. And data availability. So the data from where we are trying to do. So the data availability is one of the opportunity where we can get it for generatives, because it requires huge data to train the models, etc. And ethical consideration. These guidelines, the ethical consideration is also very important to avoid any harmful or biased content. So we should follow the ethics to get the opportunities with respect to using this generative AI. Human review and monitoring, human oversight is needed to ensure no errors or bias are present. So obviously, human review and monitoring is required, as we mentioned, and the scalability, that means expandable. So the task can be handled efficiently with available computation resources. So where we can expand this to the different level, and also it depends on the data of availability, and also it depends on the data availability. So the applications, coming to the different types of applications which can be used, which are using this generative AI. These are the few applications which have representing. So the text generation, it can be ChatGPT or GBrad. These are the few blogs or lives which we can generate the text, And also we have some other applications where we can generate the code as well. GitHub. Copilot. So, and we have code, replete. So these are the few applications where we can generate the code, and image, video generation, photographs or videographs. DALI, that's one thing which I have discussed, and Adobe, Stable Diffusion. These are the few applications again which we have for video or image generation, and other generation like voice, musician or something. So these are the few other Gamma or LE. These are the few other applications which can be used. So there are so many applications available in generative AI. See, you can use it for text generation, you can use it for code generation, and even for image or video generation or any other kind of applications like voice actors or musicians, etc. And it can be used. It can be used in healthcare. It can be used in location services, search engine services, or the motion industry. These are the few other applications which I have mentioned in the generative AI. So these are the tools available. So it's an open. So ChatGPT. This is one of the tool where many of us might be using. But still, I have one particular doubt whether it is really making us very efficient or making it very lazy in thinking wise by using ChatGPT. There is a secondary discussion. It's open for a discussion, but still there is a generative AI tool where we can get. So with respect to students, if they keep using, by seeing the language, we can easily tell what type of tool they are using, what type of generative AI tool they are using. And we can use OpenAI DALI, which is very good for images, which is very good for images. So this is how the training will happen with respect to the ChatGPT. So first, as we have seen in the previous slide, it will collect the demonstration data and train the supervised policy. So it goes with the supervised policy, and then it will start comparing the data with the trained model. So it will start comparing the data with the trained model, and then it will optimize the policy against different algorithms. It can be used, it can be reinforcement learning algorithm or different types of algorithms. So again, data collection, where it's going to train, we're going to compare the data with the trained data, and then we have the policy against different algorithms to optimize the trained model. And let's see, using a JI, a generative AI. Hope I'm not very fast, or I'm going in a normal speed. Hope everyone is following with my slides. Thank you. Okay, I'll continue. Okay, so the next one is we'll take, because we are all teachers. Basically, we are all teachers. So let me take one particular scenario in the academics with respect to using of generative AI. So as I told, DALI-E is a tool which creates the images for your course slides. You can really create a beautiful images by using this. So it can be used for your course slides or your subjects, whatever the subject which you are handling with. And ChatGPT, obviously, as I mentioned, so we are all much aware of this. So you can use the text, you can use the content which is required, whether it is a newsletter content or any other formal email, etc. So Bing chart, it is for the draft grant proposal. So what type of proposals we want to give? If you want to give any proposals, you can get the assistance from Bing chart, where we can get is similar like ChatGPT, but it's purely into the grant proposals where you can get different types of versions or different types of things to get the grant proposals. And the real world applications, I've taken some real world applications with respect to universities. I've taken two scenarios just to see what are the challenges they will face and how that can be overcome by using some AI, generative AI models. In the real world applications with respect to university and also with respect to students. These are the few things which I have represented. So study, homework, this assistance, personalizing learning plan, career guidance, research assistance, language translation, time management, organization. These are the few, I can tell few challenges or the difficulties where students will face in the real time during their tenure of education. It can be career guidance. They don't know which one to be chosen. So these are a few things, or research assistance, or they want any language translation if you're coming from different places. So these are the few things. You can see the career guidance providing advice on choosing major on career path based on the student's interest and skills, assisting in resume or cover letter writing. And also there are a few other points which tells us what are the problems we may have in these particular areas. Suppose you have research assistant assisting in gathering the research data and suggesting the resources, generating citations or bibliographies or references, etc., or translating the foreign language text and document from international students, supporting them in the exchange of programs. So all these things are a few things. In the same way, the real-time applications we may have with respect to staff, with respect to us, that is content generation, administrative support, research assistance, admissions and enrollment, very important, admissions, and emergency response and communication, student support service, website and social media management, grading and assistance, library and information. So these are the few the high-level topics where we can face some challenges. For example, you can see website and social media management, generating the content for university website, blogs, or the social media platforms, or monitoring and responding to online engagements in a timely manner. This may not happen. Sometimes you have to write the different blogs. You need to have a different blog for your content writing, for your university, or for your social media platforms. Or grading, how to assist, how to grade the students. You may have a huge number of intake. You may have 700 intake, 300. So complete for 4 years, you may have 3,000, 4,000 students. So assisting in grading the system. So these are the few things, few real-world applications in the university with respect to staff and students. Now, let's take a case study. With this particular information, let's take a simple case study. So this case study tells that what are the challenges, and if you use generative AI, what can be beneficial for the student or with respect to the faculty. So any university, any elite university, so it has a higher education institutes, it has a college admission which receives thousands of applications every year. So to improve their efficiency and provide a better experience, so they decided to implement generative AI solutions. This case study details how a college admission department generative AI to enhance their performance because they're getting huge number of applications. So it is not manually difficult and cannot it is impossible, but it may take some time. It is difficult to complete the task in a appropriate time. So the university decided to go with generative AI solution. So in this, the challenges what they have faced, in this case, the challenges what they may face is application process. It may take some time, as I mentioned, it's a time consuming. It may lead to bottlenecks or delays because it's a human interference where we are going to, as we told, speed. Speed is one of the benefit which we have with respect to generative AI. So application processing is one of the easy assignment. So admissions require significant manpower to ensure the consistency and frame of the evaluation. So where we're going to the personal statements or the what are the information which is required. So assessment is also one of the challenges where we can have an application support. what kind of support we can give to the applicant. So whether he was calling online or offline, what kind of support we can give. These are the challenges. Any admission process, application processing, any assessment or applicant support. So for these three, so what type of solution we can give with respect to generative AI? So we can have an automatic application screening, integrated AI algorithms to automatically screen and categorize applications based on the predefined category. So the generative AI system learned from the historical data, admission data, and continually refine the screening criteria. So you can train the generative AI with the data from your historical administrative data and come out with a model where it will screen the criteria. For example, if a student want to join engineering, his basic requirement is you should have attempt any competitive exam like CSE, JEE means, etc. And you should have 45 percentage minimum in computers in chemistry, physics, and mathematics. So like this, with the historical data, you can screen. So automatically, without the human interface, this application will be screened so that the effect will be less from the human, but the outcome will be more with respect to generative AI. And coming to AI enhanced assessment. So the employee generative AI can assist. The system provides initial evaluations, highlight key strength and area of improvement. So this AI generated assessment as a starting point saves time while ensuring the standardized reviewing process. Standardized reviewing process. Still, I may not tell it is this can be done for each and every assessment for a specific kind of assessment where we can have the objective types or something. So this can be a starting point. This can be a starting point where we can assist, in getting the easy assessment. And as I mentioned, support. As I mentioned, applicant support, chatbots. So if you go there, there's no need of any receptionist or anyone who is waiting for the student or the parent to walk in. So they can just come to the chatbots and they can ask any type of question. So the chatbot will automatically use a reply to you in an appropriate way. And in an accurate way. And again, it depends on how you're going to train that particular chatbot. So you can go to many universities now. There is this is AI powered based support. You go there, just I want to go to computer science department. The chatbot will reply, please go take the steps, go to 4th floor, take a right where you can meet the head of the department of a specific department. So these are the few solutions. As I told, I'm just going a brief introduction about a generative AI to get you a glance. What is generative AI? What is a generative AI? So these are a few. You make it auto screening, or you can make it an assessment, or you can make it a power application support. The best example is chatbots. So finally, we have seen the challenges, we have seen the solutions, how we can do it by using generative AI. The result will be, obviously, the application processing will be improved. It will reduce the time in processing the applications manually. So obviously it will increase and improved assessment. So the evaluation reducing the bias or encouraging the fairness. So everything can be, or you can screen it. You can screen the assessment papers, these OMR sheets, anything can be done. And so applicant experience, as I mentioned, we are going to use, if you're going to use the chatbot, so where it can assist the applicant, the student or a parent in appropriate information about the college or about the university. And increased efficiency, admission staff experienced increased efficiency as routine tasks were automated, allowing them to allocate more time to strategic data decision making. So instead of doing all these paper related work, we can think about something which how can improve the strategic decision making. So these are the few, as I told, like academic, I've taken that admission. In that admission, what are the challenges we may have and what are the solutions we can give. By using the solutions, what would be the end result? So maybe a group activity, I think you are much aware of this chart GPT. So if you are in the system, just you can open the chart GPT, just type what is my work today. So what information you will get, what reply you will get, we just check. See, because as I told, the common sense, the accurate will not be there with respect to this, because it will be trained in a very narrow way. During that only it will be. Suppose if you ask a question like, I want the contents of a newsletter, you may get an appropriate answer. Suppose if you write a question, what is my task today? What I'm going to do next? How ChatGPT will come to know about that? Okay, so that's why, like, so ChatGPT is very limited to certain kind of interactions where we can get the content in a different versions for the user. Suppose you can see for these kind of things, you may get very good representation. Write a newsletter to students about the essential student services at the university. You will get a very appropriate answer. Write a social media post about the university. Write a project plan. Write a draft mail. Yes, but if you're asking what I'm going to eat now, it will not respond, because that is not the context. That's not the context. So dependency, that's what I want to mention here. Dependency only on ChatGPT or any of these Gen AI models should be limited to a certain extent. So obviously, human brain is much more effective than any other model, but still we can use this for different versions of contents, where different types of contents which we can use. And coming to ethical concerns, as I mentioned, privacy or a biased thing or transparency, everyone may get the same type of content. So the privacy may not be there. You may think this is the content which I received, but the same content might receive to someone else. So the privacy may not be there. Transparency the lack of transparency can arise the ethical questions and about the accountability and the trust. So all these things might be few ethical concerns which may have with respect to accountability or data quality or the concept which we can. And these are the tools, platforms, softwares which we have for generative AI. Which we have for generative AI. I will list out very few, may not be all. I think in this, Microsoft, you can see the Copilot, which is covering, I think, in the day 2 session. So we are going to have a live from the industry. We invited one speaker from the industry where he will touch about the Copilot. So these are the few, as I mentioned, few tools, platforms, or softwares which we have for the generative AI. The future trend. So the future trend, obviously, the future is AI. There's no doubt for the next few years, at least. So here you can see with respect to, I can show you this one. Yes. So if you can see this particular slide. So where you can see the blue is with generative AI and the other color is without generative AI. Without generative AI. So it tells the percentage. It tells the percentage with respect to the technical capabilities or the impact that is happening with respect to professionals, educators, or creatives, etc. So this tells, you can see the occupation, like all kinds of professionals, like managers, office support. So everyone want to depend on this generative AI. Everyone want to depend on this generative AI. Okay, so you see the educator, the first one, educator and workforce training. With generative AI, it is around 54, and this scenario is taken as of 2023. So it is up to 54, So the massive dependency is happening from the educators or the training thing. So this tells what is the future and how can we use of this generative and how we are depending on this generative AI. So the future, as I mentioned, so improved creativity, ethical consideration, real-time applications, multimodal generative AIs, and hybrid models. So hybrid model, I mean, like it should be common with text, images. Obviously, now we can write the code generator is also available where we can do the solution. It can generate the code in different languages. So the creativity will be improved as a future. So the ethical should be considered. The ethical should be considered, and also many hybrid models should be. So this is the future of generative AI. So I would like to conclude here. Uh, so this generative AI is not going away. So it just started. I can tell it just started. It is in the good move. So not go away, and learn how to use it appropriately is important. So it is not coming for your job, but it can make you much more productive. So what is my experience and my thing is how we should know how appropriately to use that, in which way we can use that, and when to use that. We should not have a completely dependency. Writing a small mail, go to ChatGPT and type and get the alternate. No, when you want to use. So you should properly learn that. It's not going away. So it will be here. So only thing is you should properly use it and make more productivity through that. So being mindful of how we use this new technology and how we can shape our jobs with it help to determine the future of in an effective way. Obviously, we should upgrade with the new technology. I cannot tell, I don't know what is ChatGPT. No, we should upgrade. We should upgrade with all types of new technologies, but we should know how to use it in an ethical way. We should know how to use it in an ethical way. So thorough intentional exploration we can invite in ways we have to dream it off, and common sense will prevail in most situations. Don't blindly copy the content from the models which has been given by the generative AI. Apply some common sense, whether this content is appropriate to me, what is required for me. You just copy and paste. So these are the few things which I thought of concluding. So I have gone through just to revise. I will just take you through the generative AI, starting with evolution of artificial intelligence, strong AI and weak AI, and how the generative AI has been started, and what are the different streams it has been with respect to audio, or with respect to images, or with respect to text, or with respect to images, digital images which we have, images which we have. So all these things, and also I have shared. And also I have shared what are the challenges we have, what are the limitations we have, and also what are the benefits we have with respect to generative AI. And also I've shared few tools which are available in the generative AI model where we can use these tools. And I've taken a few one case study with respect to academics, where specifically with respect to admission. So what are the difficulties they're facing and how it can be solved by using generative AI? And what are the challenges in that? And what would be the result if you use the generative AI? That also I have briefed you. And what is the future? What is the future trend which we can follow? So there ends my presentation for today, to just to give an explore of generative AI, which will be useful for your next session, where we are going to use for the application oriented. So with respect to generative AI. So now I'm open for any questions or any discussions for all the participants. Or you can text it on the chat box as well. I think it was given access to unmute to all the participants. So if you want to ask any questions, please anything. If there is no further questions, I would like to wind up this session for the day. Okay, so I didn't get any. So hope you should have got some, at least a basic knowledge or a basic information. It doesn't mean you don't know, you might be knowing, but what is in my view, in my perspective, I try to share with all my faculty. So hope you have a very good and informative sessions today, in the morning and also today. And thanks for joining. Thank you very much.
Thank you, sir. Dear participants, that is all for today. You can join using the link that we would share for tomorrow's session at 10 o'clock, and we would be continuing from there on. Thank you for joining. Have a good day.